Okay, it's resizing. Um, I'll,
I'll try to debug it as you're going through the thing.
yeah, I'll keep an eye on this.
Okay, sounds good.
When you see me on the screen hit to on, about a minute later, you should be able to SSH in.
Okay.
It'll probably take a couple of minutes to like
Bring it up.
after
and
5 minutes
everything.
to
Yeah.
settle down,
Yeah.
and hopefully that's all it needs. And
Yeah, hopefully.
that'll be fine.
All right. Yeah, I'll take a look.
Okay, thank you. So, so with the forum, we've just been doing a quick upgrade. So it's currently upgrading, and hopefully we'll be able to have that back up again soon. And Anurag is kindly helping in the background fixing that as well. So thank you, Anurag. What I might do is I'm just going to jump into YouTube and make sure our stream is working. So if you are an international fellow and you can't access the stream, please use the YouTube chat to tell me. Hopefully it's all fine. Okay, I see that there. Oh, live streaming. There we go. Okay, looks like it's fine. Great. Okay, so we are we're going to be looking at convolutional neural networks, and convolutional neural networks are the most important architecture for deep learning. There are quite a few researchers in the field who actually think it's pretty much the only architecture we need. The other main architecture we'll be looking at in this course is recurrent neural networks, and we'll also be looking at fully connected neural networks. But convolutional neural networks actually are the state-of-the-art approach in many, if not most, areas of certainly image recognition and all kinds of computer vision, many areas of natural language processing, many, if not all, areas of speech recognition, and so forth. So this will be our focus because this single architecture is the best architecture for the vast majority of applications. But we'll be looking at the other two as well, and some state-of-the-art approaches we'll be looking at actually use fully connected or recurrent neural networks as well. So the basic structure of the convolutional neural network is the convolution. And there's this great explain visually site here. In fact, maybe we'll just go straight there and we can look at it on the web. This site has a whole range of, that's a great time to install updates. Has a whole range of like really cool animations and visualizations of all kinds of algorithms. And one of them is this convolution visualization. So the first thing to be aware of is what is an image? Right, so here's a little picture, and here's a bigger version of the same picture. And then on the left over here, if we zoom in, you can see that every pixel is just a number, right? And so this is how computers actually store images, is that they're numbers between 0 and 255, where white are the big numbers, 255, and black are the small numbers close to 0. Okay, so when we work with deep learning with images, we're working always with these matrices of numbers. So let's take a simple little 3x3 matrix. I'm going to pick this one. Here's a little 3x3 matrix. 1, 2, 1, 0, 0, 0, -1, -2, -1. Now what happens if we take these 9 numbers and let's pick a little part of this image, right? Here's a little 3x3 part of this image. And now let's take each of these pixels, and you'll see in the middle here, we're going to take each one of the 3x3 pixels values and multiply them by the equivalent 1, 2, 1, 0, 0, 0, go down a little bit, -1, -2, -1, right? So we're taking each 3x3, taking a little 3x3 part of this space and multiplying each pixel value by each one of the equivalent parts of the 3x3 matrix at the top. Okay, and then what we're going to do is we're going to add them all together. Okay, so you can see here 140 by 1 plus 66, 2, 141, 1. Live stream link is down. That's no good. Thank you. Telling me. How's our forum? It's looking hopeful. No? Oh, no, I need to, yeah, on. Okay, forum should be up in about 5 minutes. Stream is on. No dropped frames. Oh, link is good. Okay. At least it's working for some folks. Good. All right, and Anurag, you can hopefully SSH in. Can you SSH in? You can. Great. So Anurag's helping us with the forums. Okay. All right. So this is a example of a convolution, right? It's just simply something where we take some set of pixels, we multiply each pixel by some fixed value, and we add them all together, right? So you can see here's an example where we're going 118 by 1 plus 148 by 2 plus 234 by 1 and so forth, and adding them all together to get 371, right? And so then you can see on the right-hand side what that ends up calculating, right? So the white areas have high numbers and the black areas have low numbers. So what's actually going on here? Well, when you look at it, what this has actually done is it's created an edge detector, right? So you can see that the white areas are the edges of this face, right? So let's go back to the PowerPoint. So why is that, right? Well, if you think about it, if you've got a little 3x3 area where the top, above the top of it is positive numbers, large numbers, and the bottom is small numbers, then multiplying them all together, you're going to be multiplying the big numbers by something positive and the small numbers by something negative, and so you'll get a high number, right? So in other words, you're at a top edge, and vice versa. Okay, so this particular 3x3 matrix, when you go through and multiply every 3x3 area and add them up, you're going to end up with something that detects top and bottom edges. And so this particular, any kind of 3x3 matrix that is being used in this kind of operation is called a kernel, and the operation itself is called a convolution. Right? So for those of you that remember linear algebra, we're not doing a matrix product, we're doing something much simpler. We're simply multiplying every 3x3 group of pixels with each corresponding element of this 3x3 matrix. So it's element-wise multiplication followed by addition. So this particular kernel, in other words, this exact set of 9 numbers, is a top edge detector. And so you'll see back over here that there's a number of different choices. So we could say, all right, let's do a right edge detector. Right? And so you can see it's now 1, 2, 1 over here, negative 1, 2, 1 over there. And you can see it's now detecting right edges. Right? So these things you've probably played with on your computer that like change images to do various cool things to it, generally all they're doing are using these pre-defined convolution filters. So here's one called emboss, right? Again, it's a particular set of 9 numbers, which is kind of more of finding a diagonal edge. And so when we look at it, it's got this embossing idea. So that's all a convolution is. The most important thing to recognize about a convolution is it's a linear operation. It's only doing multiplications and additions. Okay? But I think it's interesting to recognize that it can kind of find interesting features in an image, features like edges. So what we could do is, well, let's think about it. What if we took convolutions and stacked them on top of each other? So had convolutions of convolutions. So took the output of a convolution and put it into the input of another convolution. That would actually not be interesting because we're doing a linear function to a linear function, which itself is a linear function. So we could have done it with a convolution in the first place, right? So that's not interesting, right? But it turns out what is interesting is if we put a nonlinear function between them. This is from Michael Nielsen's awesome work at the neural networks and deeplearning.com. Here's an example of a nonlinear function. This is called a sigmoid function. And as you can see, it basically goes flat, and then it goes up, and then it goes straight again. And as we change the values of the linear function that's going into a sigmoid function, it basically allows the whole function to like move left and right. And so by changing the values that go into a sigmoid function, we can kind of move it around. And so if we then add multiple sigmoid functions together, it turns out we can kind of create like blocky shapes like this. And then if we add blocky shapes like that together, we can kind of create interesting step functions like this. And basically it turns out, and this is like this key thing called the universal approximation theorem, it turns out if you take a bunch of these linear functions and put them through one of these nonlinearities, and then add them back up together through another linear function. If you do that with just a single layer in the middle, it turns out you can approximate any function to arbitrary complexity. This is the basic idea of the neural network. So a neural network then is simply something that has some kind of linear function followed by some kind of nonlinearity, and then we can just repeat that. Right? We can repeat that a couple of times. And so all we need to do is we need to learn these numbers. So rather than like taking some fixed set of numbers called a kernel, we're going to try and learn a set of numbers. So it actually turns out to be incredibly simple. We're going to multiply things together, and we're going to add them up, and then we're going to put them through a nonlinearity, right? And actually it turns out that the most common kind of nonlinearity is even simpler than this. The most common kind of nonlinearity, we'll talk about it more in the future, is called a rectified linear unit, and it's simply this. If you have a number that's less than 0, we're going to make it equal to 0, and if it's greater than 0, we're going to leave it as is. So in other words, it's basically max of x comma 0. That's called a rectified linear unit. Now it turns out that if you have layers where you alternate between a linear function and then max x comma 0, and then a linear function and then max x comma 0, that's basically the definition of a cutting edge neural network. And specifically, if the linear function is this, the convolution, that's called a convolutional neural network. Right? So it's like incredibly simple. We multiply things together, we add them up, and then we replace the negative numbers with 0. So what does that do? Well, remember I said we need to like figure out what these numbers are, right? And so we're going to do that with gradient descent. And we're going to learn how this works shortly, and we're going to see a little bit of data where we basically see that what's going to happen is we're going to start out with, let's say we're trying to predict these dots. We start out with a random guess, and then we find out which direction is down, and we gradually make it better and better. Okay, so you can basically see this little example here doing that. So we're going to start with a random guess as to what convolution filters we should use. We're going to create a bunch of layers of these convolution filters, and between each one we're going to replace the negatives with zeros. We're going to learn the values of the filters with gradient descent. And if we do that with enough filters and enough data, something amazing happens. We end up with a cutting edge image recognizer. And so here's an actual example, right? So these guys, Matt Zeiler and Rob Fergus, actually did this. They trained a convolutional neural network to recognize images, and then at the end they went back and they said, what did those filters look like, right? So rather than filters that look like this, right, where we've handwritten them, they just trained them, started with random, and then used gradient descent to train them. And what they found was that they ended up with filters where, here's an example of a picture of one, some that kind of looked for diagonal edges going from top left to bottom left to top right, checkerboard patterns, things that are green, and so forth, right? And so over here are 9 examples of little bits of pictures which were most activated by that convolutional kernel, right? So you can see this one is finding little bits of diagonal, right? And here's one that's finding little bits of green. So the interesting thing is that the next layer, then we truncate the negatives and replace them with zeros, and then we do it again. And so the next step is going to be able to take these features and combine them. And so the next step then found a feature which basically was able to find corners. And then there was another feature that was able to find circles, and another feature which found lines kind of more in the middle, or maybe sometimes 2 parallel lines. And so you can see here, here's examples of bits of photo that matched this filter. So it was actually finding corners. Here's one that's finding kind of curves. Here's the examples of the one that's finding circles. So again, replace the negatives with zeros, do another convolution that we're going to learn, and we can find combinations of the previous set. And so now we've got something that's finding checkerboard patterns, something that's finding kind of the edges of flowers. Already, something that's finding bits of text. So you can see like each layer, it's finding like multiplicatively more complex features. Right? So by the time we get to layer 5, there's something that's finding the eyeballs of lizards and birds. There's something that's finding dogs' heads. There's something that's finding unicycle wheels. Right? So this is the power of this, right? And this is where it can kind of be surprising. You learn this idea of like, here's how you can create something that goes multiply, add, replace negatives with zeros. Multiply, add, replace negatives with zeros. Do it a few times. Find the parameters of the linear functions using gradient descent. Okay, what next? There is no what next. That's it. Like when you do that, because there's so many of these functions and because of the power of this theoretical idea that neural nets can approximate any function, if you run that on a GPU, and remember a GPU can do many, many, many billions of operations a second. So we're just doing it at a scale that's like counterintuitively large. And so that's why this incredibly simple thing ends up being able to build incredibly complex results. So let's do it, right? Let's try this out. Let's see how it works. So you can either start following along or do it at home. It doesn't matter. Most students in the course, most of the time, tend to spend the lectures listening, and then they go home and they watch the video during the week and follow along. But if you want to start following along now, that's fine as well. So we're going to need a GPU, right? And we need a particular kind of GPU. Pretty much all computers have a GPU in them nowadays, but we actually need an NVIDIA GPU, and that's because NVIDIA GPUs support something called CUDA. And CUDA is a particular way of doing computation on a GPU that's not just limited to the kind of computations that computer games do, but general purpose computations. And so most laptops don't have NVIDIA GPUs. I don't think any Macs have NVIDIA GPUs. So generally speaking, you're going to need to access a computer that's specifically designed for deep learning or has an NVIDIA GPU. The good news is that one of the last year's FastAI students has actually built a service that allows us to instantly access an NVIDIA GPU. So we're going to start with that. So it's called Crestle. So if you go to Crestle.com, right? Yeah, if there's some that you think are necessary, then we'll start. Okay. Normally the lessons will be much more interactive than this. It's kind of, I feel like in lesson 1, we just need to get some of the basics down. So if there are questions that you don't get answered now, we'll definitely answer them afterwards on the forum, okay? Okay, so when you go to Crestle, you click sign up, and you will have a screen pop up that looks like this straight away. When you launch your instance, you'll have a choice of whether to have the GPU on or off. So make sure you have it on. So you'll have a screen here that shows GPU enabled, and here it's running. And we're paying, I think at the moment it's about 50 cents an hour or something for a GPU-based instance. In the future, this might well change, go up, go down, depending on demand, I guess. The thing that you see here is called a Jupyter Notebook. We'll be learning a lot about the Jupyter Notebook. In a survey that just came out today of 16,000 data scientists, Jupyter Notebook came up as the 3rd most important kind of self-reported tool for data science. So you'll definitely want to be familiar with Jupyter Notebooks. So rather than worry too much about the detail, let's just get straight into it. So what I'm going to do is I'm going to click on Open Jupyter in New tab, and that's going to bring up this, this environment in which I can start playing with my Jupyter Notebook. There's actually 2 things you can access through this. One is Jupyter Notebook itself, and the other is the terminal, right? So I can also click on New Terminal. So this terminal, you can see here, it's just a regular old terminal. Anurag, I am not. Is there a problem with something? Restart it?
Yeah, it's like stop the notebook.
Okay.
A bunch of people signed up.
Okay. All right, let's switch to one I prepared earlier. Right.
Oh,
Yeah. Is that something you can add more to or something?
wait, try refreshing. That's what I'm doing. You have the other one, the fast.ai.
Change to either account?
Yeah. It should work now.
Okay. Do I need to refresh or anything, or?
No, it's not great.
Yeah, I guess we haven't had everybody try to access it at the same time like this quite before, so.
Yeah.
We're,
Wait, try refreshing the page.
okay.
There you go. I think it'll show up in this.
Okay.
Maybe some people should try not to use it.
Okay, so yeah, just stop your Jupyter if you're trying to do this at the same time so I can demonstrate it. I'm sure we'll get this fixed up in the next day or two.
Yeah.
Okay. So what you'll find on Crestle is that you'll find there's a courses/FastAI and a courses/FastAI2. So we're using courses/FastAI2. If you've previously created a Crestle account before today, your account may have not had the FastAI2 course in it, in which case you'll need to git clone the FastAI repo, and the command to do that is in today's lesson thread. Okay, so you should find you can cd courses/FastAI2, and in there you'll find there's a bunch of different folders, and so in particular, if I go and I'm just going to do it straight through my account, you'll find there's a folder called courses, and in there there's a folder called DL1, and in there there's something called lesson 1. And so IPython notebooks or Jupyter notebooks have this IPYNB extension. And so when you click on them, it will bring up our notebook. And so you can see that a notebook has a combination of text, images, code, all in one place, right? Which is, you know, it's pretty nice because when you use it yourself, you can kind of document what you're doing as you go. You can put pictures, videos, HTML tables, interactive widgets, etc., all in the notebook. So it's a really great experimentation environment. The most important thing you need to know is to run a cell, i.e. to execute it, you press Shift-Enter. So if I press Shift-Enter, it runs this cell. So I'll worry about some of these details a little bit later, but the main thing to know is that we need to import a bunch of libraries in order to start doing our first deep learning training. So there's a FastAI library that's in this same repo that has a whole bunch of deep learning libraries in it, and it kind of wraps around a bunch of libraries as well. The main library that it's using behind the scenes is called PyTorch, that we're going to learn a lot about. So when I import from fastai.imports, that just basically imports a whole bunch of other libraries for us. You'll notice if you're a Python software engineer that I am not writing my code in the way that any Python software engineer would consider acceptable. It's very non-Pep8. It's very, it's kind of different. And that's because doing interactive data science is very different to doing software engineering. And so my view is that the best way to do interactive data science is to have all of the stuff you need at your fingertips. So I tend to do a whole lot of from blah import star, right? I also tend to try to write my code in a way that I can see everything I need to see kind of in one go. So I tend to put a lot of stuff like on the same line. Like I do a lot of things which are not normal ways of writing Python code. You don't have to do it that way as well, you know. You do it however you like. But you know, I definitely feel like doing interactive machine learning has a very different set of best practices to doing software engineering. You know, so you know, hopefully you find some of the things I do at least interestingly different. One of the things you'll notice also is mathematicians tend to use single letter names for their variables, ideally from some kind of language that you don't know, like Greek. Java programmers prefer their variable names to be 2 or 3 pages of code. I tend to go somewhere in between. You know, I think the idea in math that you kind of compress things down so you can look at something and immediately see what it is, like recognize the idiom, I think that's super helpful. But the idea that the letter I could mean 4 different things on the same page, I don't think is ideal. So you'll see I tend to use like short-ish mnemonic variable names. And so, you know, as we go along, you'll see like some of them are single letters and they tend to be consistent. Like if I've got the length of something, I tend to call it N. If I've got the index of something, I tend to call it I. And so I tend to use kind of short-ish names, but they're, you know, I try to, you know, give them some kind of meaning. So again, you know, my way of coding when I'm doing machine learning is very different to the kind of coding I would do if I was writing a web app, you know, with a large team of people. Which is to say, if you're trying to impress people in an interview, you know, don't code the way that I code, because a lot of them will be software engineers. Yes, it should work now. Okay, great. So then, I think maybe the most important thing to know about Jupyter Notebook is how to find out more about the information about what you're doing. And so one thing that's very handy is you can always look at the source code for something by typing 2 question marks and then write this, and then type the thing that you want the source code for. So for example, let's go down. and have a look at the function. So here are some examples of some functions, right? So if I wanted to find out what these functions were doing, I can always simply write 2 question marks and then the name of a function, and I actually can see the source code for it, right? Which is pretty amazing. 1 question mark followed by the name of a function gets you the documentation for it. You'll find that pretty much all the functions in the FastAI library look like this. They're like 3 or 4 lines of code, generally speaking. Like, we try to write things in a way where you can understand what's going on kind of pretty much at a glance, right? So they tend to be pretty short and designed to be extremely understandable. The other thing that sometimes might happen is you might want to know where a particular function comes from, or a particular object or class comes from. So like, what is image classifier data? Where did it come from? If you just write the name of something and press Shift Enter, you'll find where it comes from. Right, so it's very easy in this environment to see like where the things come from, what's the documentation for them, and what's the source code. Right, so I think those are the 3 things that you want to know. So the next thing you need to do is to get the data. Okay, so you can get the data from, and we're going to be looking at a Kaggle competition called Dogs versus Cats. We're going to recognize the difference between cats and dogs pictures. So here's a link you can get that data from. If you just use wget, you can get it. If you're using Crestle, the data's already been downloaded for you. And so all of the data in Crestle is in /datasets, right? So what I want to do is put it, have it available in the data/dogcats directory. So I just create that directory, and there's some other subdirectories that we're going to want, so I create them as well. And I just do a symlink from the datasets directory to data/dogscats. Okay. There's some other minor details we'll talk about later, which are Crestle specific. But for now, let's assume that we've got that we're either using Crestle and we've got a symlink to our data, or we've downloaded it, and so our data lives inside data/dogscats. So here is what is in that path. So in Jupyter Notebook, you can put an exclamation mark at the start of a line, and that will say this is a bash shell command rather than a Python function. So here is a bash ls. And so there's a training set, a validation set, a test set. We'll talk more about that later. And we can see then inside the validation set, there's a cats folder and a dogs folder. And then inside, for example, the cats folder, there is a bunch of cat pictures. This structure, where you have different labels, like cats and dogs, as folders, and then within each folder you have a bunch of specific image files, is probably the most common way for image data sets to be provided and shared. In particular, it's the way that, for example, a library called Keras, which is quite popular, assumes that all of your data is going to be in this format. So the basic idea is your file names could be anything you like, but they need to be in a folder which is named after the label, so named after the thing that you want to classify. So we've got a folder called cats and a folder called dogs, and in the cats folder are your cats pictures, and the dogs folder are your dogs pictures, right? So here's an example of one of the cats. And of course, that cat actually is, and here's a subset of the array, and we're going to be learning a lot more about how to create these array slices and so forth. It's a bunch of numbers, and each position of the cat is actually a list of 3 numbers, which is how red is it, how green is it, and how blue is it. Okay, so this is an RGB point. So that's our cat, and our job is to try and recognize cats versus dogs. What does it take to do that? Well, you first of all have to have the data for cats in a cats folder and for dogs in a dogs folder, and 7.78 seconds and 3 lines of code later, we're finished. And we have an accuracy of 99.2%. So that's actually all that's necessary to create an image classifier. Put your images into different folders based on what they are, run these 3 lines of code that basically won't change from problem to problem, and that's it. And we're going to look at all of these steps in a moment, right? But if you go home and get some different data set that has different images in different folders based on what they're pictures of and run those 3 lines of code, you will now have an image classifier. How good is this? How good is 99.2%? Well, this data set was originally a Kaggle competition, and we'll talk about more about Kaggle shortly. And it was in 2013, is that right, Yannette? 2013? And in 2013, before the competition was launched, the state-of-the-art accuracy was 80%. Generally speaking, when people launch a competition to try to improve something, the state-of-the-art gets killed, as happened this time. And the winner of this Kaggle competition got 98.3%. So the short answer is that in 7.78 seconds, we've built a classifier that was better than the best computer vision experts in the world were able to create in 2013. So not bad, right? And so when you hear people say, you can't do anything useful with deep learning unless you have Google scale infrastructure and Google scale data, just remember what we just did. I think we have, let's take a look here. So we have how many images? So we could go actually, let's just go ls valid cats pipe wc minus l. So that's a valid we need for train. Okay, we've got 11,500 cats and 11,500 dogs. Okay, so with about 20,000 images and 7 seconds, we were able to create a state-of-the-art, as of 2013, image classifier. So when people say you need Google scale data and Google scale infrastructure for deep learning, that's kind of a meaningless thing to say. What they really mean to say is, like, if you're working on exactly the same problem that Google is, and you're using exactly the same algorithm as Google is at exactly the same time, then if they train on more GPUs with more data for longer than you did, they'll get a slightly better result. But if you want to get like a good result on your problem, it's very likely you'll be able to do it using a single GPU in a very small amount of time. And so that's what we're going to be doing. Throughout this course, we're going to be getting a whole bunch of state-of-the-art results using a single GPU in somewhere between a few seconds and a few minutes, sometimes a few hours. And so that's what we're going to be doing for lots of different types of data, lots of different problems. So we've created our model. And so when you try this on Crestle, Crestle's actually a bit slower than this, particularly the first time you run it. Crestle has to basically pre-compute some information, which takes a little bit longer. So on Crestle, this might take a minute the first time you run it. Also, Crestle's running on some older GPUs, so that even the second time you run it, it might take 20 seconds. I'm running this on a 1080 Ti, which is a graphics card that costs $600. This is how long it takes on a $600 graphics card. So one of the key things we need to be able to do then is to kind of understand our model. Like, so we know that it's 99.2% accurate. That's what this last number here means. But what's it doing? And so the best way to understand a model is to actually look at the results of it, right? And so one of the things we'll learn in this course is that you can learn a lot about a data set by analyzing what the model tells you. So another common refrain about deep learning is it's a black box that you kind of can't look inside. That's definitely not true. In fact, we've already seen that it's not true, right? Like these pictures we looked at, we were actually able to look inside and see what a model's looking at, right? So there's all kinds of interesting ways of looking at a model. We're going to look at something really simple here. Let's start by saying for our data, what is the y, that's the dependent. So when I say y in my code, I pretty much always mean the thing you're trying to predict. Anytime you see VAL, that means validation. So this is the label of my validation set. And so here's what, it's a bunch of zeros and ones. Okay, so we started out with a folder called cats and a folder called dogs. The FastAI library automatically turned that into a column of zeros and ones, cats and dogs. It automatically figured out what classes there were based on the names of those folders. So it said there's a folder called cats and there's a folder called dogs. So cats are going to be 0 because it's the first one here. Dogs are going to be 1s. And yeah, so you can have as many categories as you like. It'll all work automatically. So have as many folders as you want. So then if you, so just to go back up here, we'll look at this in more detail, but we've got the data sits in an object called data. The learner, this is a concept specific to FastAI, it's kind of like the model, sits inside something called learn, right, which we fitted. So the model called learn, we can call .predict to get our predictions for the validation set. By default, they actually return the log of the predictions, and we'll see why during the course. But for now, just know that we have to go exp, so e to the power of, to turn them back into probabilities. So what we can do is, with these two cells here, the details don't matter too much right now, but what we could do is now we could grab a random subset of ones which are correct. So true here means correct. So here's a random subset of some pictures along with their probabilities. So remember 1 was dog. So this here is saying I'm pretty sure it's a dog. And 0 was cat. This is saying pretty sure it's a cat. So here are some examples of some which were correctly classified. We could grab a few that are incorrectly classified. All right, so here's some that are incorrectly classified. So this one's interesting, right? You can see that, like, by running a model and then analyzing its results, it's actually a great way to do data cleaning. Like, a lot of people say, I can't do any deep learning until I've cleaned my data. Whereas my approach is always to build the model and then use that to clean my data. Like, not use it to clean my data, but use it to tell me what data to clean. So when you see like which ones were getting incorrect, that is often actually going to show you which ones have something weird going on, right? So this is a good way to do data cleaning. You can see that this model is incorrectly classifying some things which it probably should be getting right. Like that looks to me like a cat. This one's not obvious to me what it is, and interestingly, it's got a 0.5 probability. So this one, the model's saying, I am pretty sure I don't know what it is. So that's actually pretty good. Like, again, it's something you can find out from the deep learning model is which ones don't you know how to deal with. Particularly interestingly, we can say which ones are the most correct. So these are the most catty looking cats. Which ones are the most correct dogs? So these are very doggy looking dogs. Which ones are most incorrect? So this is interesting. Here's one which absolutely should have been a cat, but we got very wrong. Right? So again, good data cleaning. Right? These ones here look like genuine mistakes from our model. Okay, so here are the most incorrect dogs. And this is interesting. We'll talk more about how to fix this problem in a moment. But in short, the original images were rectangular in shape. Our library, in fact, most deep learning algorithms tend to assume that you've got square pictures. So our library, by default, cropped out the center, right? The center of the rectangle, which in this case didn't really have the information it needed. So we'll learn about how to deal with that. And here are the most uncertain predictions. So here are the ones where we've sorted by how close to 0.5 the probabilities are. And so here's a good example that appears to be a dog and a cat. So I'm glad the model correctly figured out it actually doesn't know what it is. So, like this is, you might have noticed like the first thing that we showed you after showing you like how to train a model is how to look at it, right? Like it's not all about creating something that's as accurate as possible, but about understanding it, right? So when during the week you go back and you look at this code, you know, which is in the end basically 1 to 6 lines of code to actually do these visualizations, and none of this, this is all just using standard NumPy. Hopefully you'll kind of see how you can start to play around with data sets and understand the models yourself. So one of the things you might have noticed in our 3 lines of code is that there are 2 magic numbers. So the next thing we need to show you is how to pick the numbers, right? In addition, there's a word here which we need to talk about. This here refers to the architecture of the convolutional neural network. So it turns out there's quite a few different ways of actually constructing a convolutional neural network, and we're going to learn about during this course. One of the things you need to do when you do this in practice is to pick one of these architectures. The standard thing you'll hear a lot is that these details about like what architecture you pick and all the parameters, that we call them hyperparameters, which we'll learn about, like that you have to choose, is some kind of very complex thing that takes a long time to learn. It turns out that's actually largely not true. So for one thing, the fact that we've only made you choose 3 things: an architecture, a single number here, this is called the learning rate, and a single number here, this is called the number of epochs, is because we've already figured out automatically all the other things that you need basically for you, right? And again, we're going to see them all in detail during the course, but interestingly, it actually turns out that most of the, in fact, pretty much everything you need to choose to train a good neural network are things that there are you can either automate or you can provide very clear guidance on. So my first guidance is this. For computer vision, most of the time, this particular model, ResNet34, is probably what you want to start with, right? And is probably all you need to end with, right? So I use this all the time. And it's fast and it's accurate, and so, if you can't get a good result with ResNet34, something else is your problem, basically. Yeah. Does ResNet34 do hot dog or no hot dog? It sure does. As long as you have enough examples of hot dogs, including Chinese hot dogs and all the other kinds of hot dogs. So that's, first thing you pick, and I would just say pick that, right? The second thing to pick is this number here, which is called the number of epochs. This is how many times do you want the algorithm to read each of your images? So how many times should it go through the whole set of images to learn from them? And, I would start with 1, right? Let's see, if just reading all of them just once, does that give you a good enough answer or not? And if not, you run more. Okay, and we're going to see this in a lot of detail, right? But again, basically you can just start running 1, see how it goes. You can run it a second time, you can run it a third time, and see how it goes. The only one that's actually kind of in any way complex to pick is this one here, which is called the learning rate. Again, we're going to see this in a lot more detail, but in short, the learning rate is this thing where I said, with gradient descent, you have to figure out which way is downhill and take a small step in that direction. So mathematically speaking, and we're going to look at this in detail later, we take the derivative of the function. The derivative is which way is uphill. The opposite is which way is downhill. And then the learning rate is what do we multiply the derivative by? right? So if you take a big step, you might go way beyond where you're trying to get to. If you take a small step, eventually you'll get there, right? But it'll take you lots and lots of steps. So what do you multiply the learning rate, sorry, what do you multiply the gradient, the derivative by, is a really key question. And that's called the learning rate. And this has been like perhaps the biggest challenge for practitioners, is like figuring out what learning rate to use. So here I picked 0.01. Why did I pick 0.01? Well, it turns out that this really amazing researcher created a paper called Cyclical Learning Rates for Training Neural Networks, Leslie Smith. And in it, he almost in passing showed a totally reliable way to set the learning rate pretty much every time. And I'll show you what it is. So here we're going to create our learner again from scratch. And this time, rather than going learn.fit, I'm going to go learn.learning_rate_find. Let's do it from scratch. Right, so create our new learner, learn.lrfind. Okay, it took less than 2 seconds, right? And after that, we can call plot learning rate. And what it's done is each iteration, so it's gone through the whole data set once, and looked at a few images at a time. It's called a mini batch. And each mini batch, it's gradually increased the learning rate. So it started with something tiny, right? So small it can't possibly jump too far, right? And it gradually increased it, right? And eventually it gets to the point where it's jumping way too far, right? And so what we can then do is we can plot the loss, so the basically how much error is there, against the learning rate. And so as the learning rate increases, at first the learning rate's so slow it basically doesn't improve, right? It's taking tiny little steps. By the end, it's taking 2 bigger steps and it's getting worse. But in the middle, it's getting better. So what we want to do is pick the largest learning rate where it's still clearly getting better. So in this case, like at 10 to the negative 1, so that's 0.1, it's kind of flattened out. So here, it's clearly getting better. So the loss is kind of, and we're going to learn a lot about the loss, but it's basically how much error is there. So the goal is always to decrease the amount of error. And actually loss can be defined in lots of different ways, but in general, it refers to how much error is there in your model. So the goal is to improve the loss.
The loss after the first epoch, or what?
So this is showing us the loss after every single step, after every single mini batch. So we actually didn't even end up doing a whole epoch. We didn't even go through all the data once. We basically picked 64 images at a time, and after each 64 images, we found out what the loss was. And again, we're going to be going through all of this in detail, mini batches, epochs, and so forth, right? So as we went through, and so you'll actually see here, it actually only finished 81% of an epoch, and that's because by the time it got the learning rate up to 1.2, the loss had already been getting worse quite a bit, so it stopped looking. So for you guys that, for the people here who are totally new to deep learning, all you need to know is this. You call lrfind, and then you call plot on the learning rate scheduler, and you find the point at which it's still clearly going down, and that's your learning rate. So I picked 0.01. Right? So as you can see, all of the now steps, all of the things to pick for these 3 lines of code, we now know how to do it, right? ResNet34, just do that for now. We'll learn more later, but it's nearly always a pretty good choice. For learning rate, look at that picture we just saw. And for number of epochs, start with 1 and run more as necessary. So, excuse me. So we're just about out of time. And so I'll just finish off by mentioning a couple of things. The first is what to do this week. So in general, oh, sorry.
People are having memory issues. Can you show how to change the mini batch size so that people can run their notebook?
Okay, so your GPU has a certain amount of memory on it, and if we try to pass in too many images at a time, it will run out of memory. Right? And the amount of images you pass in at a time is called the batch size. So the GPU I'm using here has 11 gigabytes of memory on it. The ones on Cresol and Anurag, I think, are 16 gig? 12 gig? Oh yeah, 12 gig. Okay. If you're using a GPU with less space on it, you might be getting errors, in which case you need to use a smaller batch size. There's no particular harm to using a smaller batch size. It's just like if at the moment I'm giving it 64 images at a time, if I change it to 32, it's going to have to do twice as many batches. So I'll show you a cool trick. In Jupyter Notebook, you can hit Shift-Tab. And Shift-Tab pops up this little window showing you all of the parameters that you can take. And you can see here I've got, and I always use this particular abbreviation. BS is batch size. So here the batch size by default is 64. So if you've got less memory on your GPU, you would just type BS equals 32. Okay? If you ever run out of GPU memory, you'll get an error saying, tried to allocate CUDA memory and failed. Change the batch size and restart your kernel. Like once it has one GPU error, it doesn't recover gracefully from it. So if you go up to kernel, restart, okay, and then you'll just have to go back and rerun all of the steps up to there, okay? So what I suggest you try and do, yes? Is there a reason why batch sizes are a multiple of 2? Computer scientists kind of like counting in multiples of 2. It feels more natural. There's not a really good reason. The thing I find kind of handy though with multiples of 2 is if I don't know how big to make something and I start out making a multiple of 2 and it's too big, I can divide it by 2 as many times as I like. That's like it, you know, there's no particularly good reason, honestly. Okay, so what I suggest you do this week is to, if you haven't used Jupyter Notebook before, like play with it, right? And one cool thing is you can use Cresol, and if you don't turn on the use GPU switch, then you're paying like, what is it, Anurag, like 3 or 4 cents an hour? 4 cents an hour, right? And you can't like train neural nets with that, but you can play with Jupyter Notebook, right? You can create a new notebook and just get the feel of it. The most important thing to know about Jupyter Notebook is the H button. You press H, it tells you all of the keyboard shortcuts. So this is how to do everything. And I find over time I kind of have got to know all of the keyboard shortcuts. They're all really useful. So I'd say like get to know Jupyter Notebook. Try to make sure that you can run all of these steps in Cresol. Remember, if you're going to run these steps in Cresol, you do need to have the GPU switch turned on. And try to like look at some pictures, right? So like try some of these things where we're actually like looking at the value, looking at the labels, looking at the classes. And so if you want to see like, well, what else can I do? Well, type data dot tab, and it'll list all of the things that are inside that object. So you can like see what else is there, you can play around with it, you know, and think about what other kinds of things you might want to plot. Maybe you could try using different learning rates. So like, what if you tried a learning rate of 1e neg 3 rather than 1e neg 2? How much slower is it? Is it slower? What if you used 0.1? Does it train at all? You know, what happens? And then finally, what we're going to look at next week, I'm going to look at a number of things, but one of them is this thing called data augmentation. And with data augmentation, what we're going to do is each time the algorithm sees like a cat picture, it's going to see a slightly different version of it. Sometimes it'll be pointing right, sometimes pointing left, sometimes it's going to be rotated slightly. This one you can see it's slightly more to the right, this one's slightly more to the left. With data augmentation, we're basically changing the images a little bit each time so that the algorithm is getting different versions of it. So it's kind of learning to recognize, you know, what a cat looks like in slightly different ways. And so like you can read ahead if you like and try it. Like to add data augmentation, it's literally a case of just adding these two parameters to our original command, and then you run exactly the same things, right? And you can kind of like play around with that. So yeah, feel free to kind of read ahead a little bit. The other thing you might find interesting, and again, we're going to look at this next week, is you could look at lesson 2. And what you'll find is in lesson 2, we're going to take a different data set, one which is satellite images, which has multiple labels. So this one, it's got both weather, like hazy versus clear, and also what's in it. So in this case, it's got some water, primary, and agriculture. And you'll see that we'll use the exact same 1, 2, there's the LR find, 3, so exactly the same 3 lines of code, and we're going to have a state-of-the-art satellite imagery classifier. And you'll see that in order to figure out what learning rate to use, we'll use exactly the same 2 lines of code for that. So if you want to like look ahead, you can kind of get a sense for how exactly the same steps work for recognizing images of the Amazon rainforest from satellites as they do for recognizing cats versus dogs. And so then this next week is what we're going to be looking at in a lot more detail. Okay, so thanks everybody. This week, you know, I guess from now on, like pretty much every lesson is going to be entirely running and looking at code. You know, and then looking at what that code does, and then looking at kind of the theory of what it's implementing behind the scenes. And see you all on the forums. Thanks very much. Bye-bye.